Michael Faraday invented the first electrical generator. It was a DC generator, and it consisted of a copper disc that he could turn, and he had a magnet such that there was a magnetic field going through the top of the disc here. And then he had these brushes that laid across these 2 points, so they made an electrical contact but allowed the wheel to be turned. And when he turned the wheel, he saw that on his meter there was a current flowing. So these X's are representing the magnetic field going into the copper disc. Because of the mechanical motion of the disc, the electrons in the vicinity of the magnetic field have a velocity to the right, and I'm showing one of those electrons here. So the electrons will flow like this. There was a lot of excitement about Faraday's invention of the electric dynamo, so much so that the Prime Minister of England, Robert Peel, stopped by to see what all the fuss was about. Peel asked Faraday what the use was for his invention. Faraday replied, "I know not, but I wager that one day your government will tax it." Now, you could also use Faraday's law to explain the operation of this generator. It's just a little bit easier to look at QU cross B to see how the electrons will flow in this example. Electromagnetics are completely described by these 4 Maxwell's equations. But you don't see the Lorentz force equation in there, but it's actually contained inside these equations. In fact, it can be shown that Faraday's law is equivalent to the Lorentz force equation. Let's look at how AC generators work. So here I have 2 magnets. So this would be like the North Pole and this side a South Pole. And then I have a coil in here that I can turn. And there's electrical connections to the coil, so this side of the coil rubs against this ring, and this side of the coil will rub against this ring. As you rotate this coil, the amount of magnetic flux going through the coil will vary. This variation in magnetic flux in the coil will result in an AC voltage appearing across the 2 rings. We have a coil whose axis of rotation is along the x-axis, and there is a magnetic flux density field in the z direction. So as the coil rotates, the amount of magnetic flux going through it is going to vary. Here's our x and y axes, and here's the magnetic flux density field coming out of the page, and our coil will rotate about the x-axis like this, and so the number of those dots representing the magnetic flux density field coming through the coil will be a maximum at this point, decreasing to 0, and then starting to increase again, but in the opposite direction through the coil, and so forth as the coil rotates. Here's a view looking down the x-axis at our coil. The coil is rotating like this about the x-axis. Theta is the angle between the outward normal from the surface and the z-axis. It is rotating with an angular velocity of omega, so the angle theta is equal to omega times time. So if I form this right triangle where the coil's surface is the hypotenuse, this angle in here is also theta. The value of this side of the triangle will be the surface area that's perpendicular to the flux. That will be S times the cosine of theta. The magnetic flux going through the coil in the z direction will be this surface area, S cosine of theta, times the magnetic flux density field in the z direction, B sub z. Substituting omega t for theta, we have an equation for the sinusoidal variation in the magnetic flux through the coil. Let's apply Faraday's law. We'll integrate in the direction of the arrows here, so putting your right fingers in the direction of the arrows, your right thumb points in the z direction, so this will equal minus n, the number of turns of this coil, times d psi dt in the z direction. Assuming negligible resistance in the coil, the integral of E dot dl will just be the voltage drop across our gap. For psi sub z, we will substitute B sub z s cosine of omega t. B sub z and s are constants, so they can be removed from the differentiation. So we perform this differentiation, we get minus omega sine of omega t. The voltage that drops across the gap is sinusoidal with the frequency with which we're turning the coil, and it's proportional to the frequency you're turning the coil, the surface area of the coil, the magnetic flux density field in the z direction, and the number of turns of the coil.